And in that discussion, I believe we established that there are two types of kinetic energy. There's translational kinetic energy, which deals with an object changing location, something that center of mass is moving from one place to another. And there's rotational kinetic energy, something that is spinning. Clearly, an object can have both of these at the same time. But what's important to understand is that these can be completely and independently happening to an object. Now, you throw a frisbee, it is going to be spinning and moving through space. Those two things are not connected together directly, but they both contribute to the total kinetic energy of the object. At this point, we have lots of energies that we could talk about, right? Gravitational potential energy, all the different forms of kinetic energy, elastic potential energy. There are lots of forms of energy out there, and we only have 4 in our disposal. There will be a few more added to this list, and there's a few more that you already know about, like chemical potential energy, the energy that's stored in chemical bonds between atoms. We talked about at the beginning of the year that there's thermal energy, there's energy inherent in something's temperature. These are all different forms of energy. The usefulness of energy depends, and in some cases it's hard to get useful work out of the forms of energy that exist. That's one of the things that we try to do as humans, is find ways to get useful work out of the energy forms that we have at our disposal, because we don't want to do the work. Well, we want to get in our cars and have it take us places. Well, that's trying to find a way to have something else do useful work on us from some other form of energy. Generally, that's going to be some kind of chemical energy or thermal energy. A few of you have some kind of stored electrical energy, and there is electrical potential energy out there, ways of storing energy in a form that can be used later due to the electric fields and magnetic fields in space. These are all just different forms of energy. But when we talk about energy of motion, this is going to be it for us. We're going to add those two together, and that's going to be the total amount of kinetic energy. Will be the sum of the rotational and the translational kinetic energy. Sometimes these things are linked together and sometimes they're not, and we'll talk about situations of both. So we're going to do several examples today to kind of highlight what it means when we say using kinetic energy in problems. We're going to go back to a good old standby because it's an easy kind of low impact first starter. We're going to talk about the things on the ramps. Why? Because we just finished a test on it. So all of you are masters at it. So we'll start by placing a disc on top of a ramp. We'll let it roll down the ramp. Now, we have talked about objects sliding down ramps a lot. And one of the things that we did first semester is we built up a whole idea of things on a ramp, and we dealt with forces first, then energy afterwards. Should sound familiar to you all. Well, we're going to kind of come back to that. We already dealt with the forces acting on this object, and for it to roll down the ramp, much to some of your displeasure, the frictional force is going to have to be this way. You didn't necessarily say this on the test, but this is the truth. If we want the object's rotational speed to increase in this direction, it's going to require a torque that is in this direction, right? The same direction as the direction you want it to spin. And that can only happen if the frictional force is angled up the ramp. There are two forces that are acting to bring the object down the ramp. There is the gravitational force trying to help it get down the ramp, and the frictional force working against it getting down the ramp. We already know this. Now, if the object were to slide without friction, then you could figure out at the bottom how fast it's going by either calculating its acceleration down the ramp and using a motion equation to figure out how fast it's going at the bottom. We've done stuff like that before. But you also are aware that if the object started at the top of the ramp, it would have gravitational potential energy. And if it makes it to the bottom of the ramp, it would have kinetic energy. First semester, we never dealt with rotational energy. We just assumed things slid down the ramp. But now, if an object has friction acting on it and is capable of rolling because it's the correct shape, then it will have two forms of energy when we make it to the bottom. Two forms of kinetic energy, translational and rotational. Now, that alone should be enough for you to recognize that the object's going to be going slower than if it slid without friction. That should be enough. You know this because of two different reasons. The first reason we talked about in the last unit, that's going to be going slower because there's a frictional force acting on it, and that frictional force acts in the opposite direction of motion. So one of the reasons an object that's rolling will be slower than an object that slides without friction is because there is a frictional force. But the second reason, and maybe the one that's easier for some of you to understand, is that if an object rolls down a ramp, it has to split up a finite amount of energy into two different places, and it didn't have to do that before. Since it starts with the same amount of energy as a block, but because it rolls, that energy has to get divided up. When it gets to the bottom, some of the energy that would have been in translational now is in rotational, so it's going to be going slower. So, prove it. You guys are smart enough where you don't need me for this. An object rolls down a ramp. Let's say it's a disk with a moment of inertia of 1/2 mr squared. Tell me how fast it's going. I want the linear speed at the bottom of the ramp if it rolls down the ramp. I keep using that word. Why? You know why. I'm trying to trigger a memory for you, something that you get to use when something rolls. So an object rolls down a ramp, you tell me how fast it's going, and I want my answer in terms of m, g, and h. You don't have to use all of those, but you can't use anything else. So no r's in the answer, no i's in the answer. If I want to know how fast it's going, I'm solving for v, correct? But is it clear to you, and I'm not sure if it is, and I'm just using you as an example person, right? It's like it's like just the two of us are talking. Like there's no one else in the room. That way I'm not nervous about them. All right. Is it clear to you that the faster it's moving, the faster it'll be spinning too? Okay, so we know that we probably are going to have to put it either all in terms of how fast it's spinning or how fast it's moving. So which one did I ask for? How fast it's moving. So I want to get rid of the spinning part and put it in terms of the moving part. There's our first thing. That's the right answer. That's one of the first things we're going to do is we're going to get rid of that omega and put v over r. So everything's in terms of how fast it's moving. And we can do that because of a single word that I said in the problem. What's the word that I used that said I could do that? I even wrote it there. I did. I wrote it someplace on the paper. Oh, you did say rolling. Okay, thank you. So yeah, because I said it's rolling, we're able to use v equals omega r, right? Because it's rolling. That's why that substitution is there. That's not F though, right? If it's rolling, it's spinning. That means that something about its inertia has to be brought up too. That's I. So we have to put a statement in there that's about the disk. Because if this were a ring, it would behave differently. So we have to put something in there for that. What am I going to do with that, Daniel? And what is that? 1/2 mr squared. Excellent. I'm glad you memorized that. That's important. I mean, it's not there. So, all right. So it looks to me like the r's cancel here. Do you guys see that again? Not uncommon, but not necessary. There are situations where that may not happen, so be prepared for them. Don't assume. All right? But since I didn't let r in the answer, I kind of knew that was very likely. So 1/2 mv squared plus 1/2 times 1/2 is 1/4 mv squared equals mgh. There we go. So not bad, right? So we're just going to combine terms, get 3/4 mv squared, cancel out the m's, and get 3/4 v squared equals gh, and then we are right there. Now, when we rolled the disk and the ring down the table, which one got there first? Disk. So prove that the ring will be slower. This is for all of you who don't practice a second time. So let's practice a second time. You'll probably need to know the moment of inertia of a ring, mr squared. That'll help. This is the disk. You redo the whole problem and do it for a ring. You'll find that at the bottom, you get square root of GH. Excellent work there, folks. Is it clear the ring is slower? Yes, 1 is definitely smaller than 4/3, right? Because there's an implicit 1, or yeah, an implied 1 there. Now, the thing I want to bring up here, and are you ready for a trick question? It's clear the ring is going slower than the disk, right? Clear. And you guys did the problem, so you know. Which one has more energy at the bottom, the ring or the disk? I mean, because obviously the disk is going faster. So which one has more energy at the bottom? Why is it the same, Oliver? That wasn't one of my choices.
Because they both have the same energy starting out.
That's right. Just because I didn't give you that choice doesn't mean it's not the right one. They both started from the same height, they both are the same mass, and they both had the same amount of energy. So even though one is going faster at the bottom, they still have the same amount of energy. The energy is split up between the kinetic rotational and the kinetic translational. It's the same amount. So even down there at the bottom, their total kinetic energy is still mgh, because that's how much energy they started with. We got it? All right. I'm going to try and trick you again. You are easy to trick. So let's do that problem again, because I do believe in practice. So let's get that disk, and let's have a ring too. There we go. So I have my ring and my disk, and I roll them towards the ramp. So I give them the same linear velocity, and I roll them at the ramp. Which one goes higher? The ring or the disk? I'll give you the neither as an option, or you can say the ring, or you can say the disk. If I roll them at the same speed, which one makes it higher up on the ramp? I did say rolling, so I'm not trying to trick you there. Now, I can ask this question several different ways. I asked it based on height. I said, which one goes higher up on the ramp? I could say which one goes further along on the ramp, but you understand that's the same question, correct? But I could also just ask you which one has more energy. I roll them both at the same speed. Do they have the same energy if they have the same velocity? Now, if you're guessing at an answer, you understand that the very next thing will be explain, right? So it's hard to guess. And I'm not trying to trick you. I'm trying to make you think here. But one of these is harder to turn than the other, which means it's going to take more work to change its kinetic energy, right? We're using the right language here, because work equals a change in kinetic energy, whether we're talking rotational or translational or both. Since the ring is harder to turn, it will take more energy to get it turning. So if I want to get it to turn at the same rate as the disk, it's going to take more energy. It will have more energy. Therefore, the ring will go higher up along the ramp than the disk will, because it has more energy. These problems are not hard, but we often jump at our answers. And we jump at answers that seem right. But at the bottom, if they're both traveling at the same speed, the ring has more energy than the disk. Now, if I give them both the same amount of energy, which one will be going faster? Sure, the one that won the race going down the ramp. I gave them the same amount of energy at the top of the ramp. And which one made it down first? The disk. That would still be true on the ground. If I gave them the same amount of energy on the ground by just rolling them, the disk would be going faster than the ring. So imagine if you have a spring launcher like we had for all those boxes, and we pulled these back against a spring and launched it. If I pull them back the same distance against a spring and launch each of these separately, which one will be going faster off the spring launcher if they roll? It'll be the disk. Now, they probably will slide. If there's no friction, that changes this, correct? This is only true in situations in which it's rolling. If they're sliding, we don't know because we don't know how much of the energy is going to be transferred to rotational. And sliding doesn't mean they don't roll at all or don't spin at all. It just means that their spin is not linked with their motion.